the first thing that I wanted to do is, well, we left off here at the end of last lecture, and I'm going to give you a heads up. I'm going to go off script a little bit. The slide set that I gave you does not contain this content. So if you're looking for what I'm about to write here, you are going to be sorely disappointed. But it was inspired by the question about power spectral density and autocorrelation. So come with me on a journey into random processes. Now, 525 students are gonna kind of yawn or roll their eyes at how I'm about to treat random processes, but I think undergrads have not been exposed to these. Is that true? Do you talk about time varying random variables in Stats 350?
Or like 2 days maybe, or like a week.
Okay. Okay. So then you haven't, it's not a new concept that we can, in addition to talking about random variables, we can talk about random variables that vary with time. And so the common way to think about random processes, well, one way that I like to think about them is kind of as having two dimensions. So commonly there's the time dimension, but also, if you like, there's kind of like a lottery dimension. So this is the randomness dimension, that if I run a lottery and the results of that random experiment are blah, then that puts me here, which results in some time varying function. Now, I can run the lottery again and I might get a different result, which varies with time in a different way. And I can run it again and I'll get a different result that varies in time a different way. Now that's running the lottery and then letting the result play out in time. You could also flip that statement. You could fix time, and then what you would get is, if you viewed this in this direction, is you would get a random variable, right? You would get a quantity whose result depended on a lottery. And I'm using these loose terms like lottery because I actually don't want to get into the weeds of like atomic decomposition of probability space, but I hope the word lottery kind of comes with all the meaning that I hope that you garner from it. Is anyone confused by that term? So if you look at it from one dimension, it looks like a function or a signal. Wow, that is terrible. If you look at it from another direction, it looks like a random variable. Okay. So what I have been doing when we talked about that random bit stream is saying that at every instant in time, there are actually only two options, two results of the lottery, right? So you could also do some analysis, do some operations on this random process in either of the two dimensions. You could think about averaging in this direction, which would mean for a given time, what's the average of the random variable at that time? Or you could think about averaging over this direction, which is over time, what does the function do? Which the result of that would be a random result. Okay, so you could also talk about, so in the parlance of your random processes, this would be m of t. And this would be the integral of 1 over t x of t dt. Okay, this guy is called an ensemble average. Whereas this one is called a time average. Furthermore, you can start talking about how these things compare to each other. And that's where we get into autocorrelation. Okay, so you can talk about autocorrelation across, for a given time, across values of the different possibilities of the lottery. So think about this in terms of variance. Or you can think about autocorrelation in the time domain. So, and this is the one that I've been talking about. This would be Rxx of t from the last unit, last module. And I admit that it sounds confusing to talk about the autocorrelation of the ensemble and the autocorrelation in the time domain. Now, for our class, and for the random processes class for 525, that's their bread and butter, is analyzing when those things are different and when you have to keep them straight. But for our class, we are going to make our lives much easier by only considering ergodic random processes. Now, this is a good vocab word for your pub quiz. I actually don't know. Don't go to pubs. You'll get coronavirus. An ergodic random process is one in which the time statistics equal the ensemble statistics. Another way to say that is, it doesn't matter, right? The autocorrelation is the autocorrelation. It doesn't matter if you got there by doing variances and covariances, or if you got there by doing convolutions. Okay, so this is going to be where we restrict our attention. Lest you think that all random processes are like this, they're not. But I think that you will address that in its gory detail in 525. Okay, so this is why I bring all this up. It's to get us to the following statement. The question on Piazza was, I don't understand the connection between autocorrelation and power spectrodensity. So let me bring in a very popular example. If I say to you that I have a process, a noise process, and it is white, so white noise, what does that connote? And this is a non-rhetorical question. I would like feedback from the class. If I say white noise, what does that mean to you? What picture pops up in your head? What phrase appears?
Just a straight line on the frequency spectrum.
Okay. So someone thinks about a straight line on the frequency spectrum. Awesome. And that could be power spectroscopy, or it could just be Fourier transform. But the idea is we give it the name white noise because it has equal power at all frequencies, right? You've heard that explanation. Anyone have a different take on it? How about this?
Oh, sorry.
Go ahead, please.
Oh, toward like in terms of like random processes, I guess I forgot necessarily what was a random process, but it had, well, I guess it was just like a random process in some sense that had no correlation.
Ooh, that's the word I was looking for. If I have a white noise process and I sample it now, and I sample it now, does information of one tell me anything about what I'm going to get at the other? Does it matter how far apart in time I snap my fingers?
No.
No. So if you want, it helps sometimes to think about this in discrete time, that if I sample the process at regular intervals, that the sample at time n tells me nothing about the sample at time n plus 1. All right, that's another characteristic of white noise, is uncorrelatedness in time. So if we look at x of t, and it's a true white noise process, right? This is clearly a white noise process. If I were to shift x of t by an epsilon amount in either direction, how much area would be under the product of those two curves? Remember, x of t, this white noise process, jumps around. It jumps positive, it jumps negative. And if I shift it by any amount, we've already established that knowing it at any point in time tells you nothing about any other point in time. Can you see that if I were to shift a copy of this function by just an epsilon amount, that all the areas would end up canceling? If you look over a long enough time span? Okay, so I think what my claim is that, and remember, autocorrelation is a function of the shift. So if we shift it a little bit, we should expect 0 correlation. If we shift it a lot bit, we should expect 0 correlation. Now that's true in either direction. What if I don't shift it at all? How much area do I expect?
Infinite.
Infinite. Because if I don't shift it at all, then all of a sudden I'm basically squaring the signal. And so everything that was negative flips up positive, and I get an infinite amount of area. So we have a name for a function that is 0 everywhere, except at 0 where it goes to infinity. We call that the Dirac delta function. And what's the Fourier transform of a Dirac delta?
A line.
A straight line in the frequency domain. Okay. So I'm trying to appeal to your gut instinct that a white noise process, which you know has a flat spectrum, and you know is uncorrelated in time, those two things are Fourier transform pairs. Okay, so this is another perspective on why autocorrelation tells us about power spectrum. I always like this. This connection was very good when I first made it. It felt good. Any idea what might contribute to the magnitude of the power spectrum? Well, certainly it has to do with the magnitude of how big of an infinity are we talking about here in the autocorrelation?
Maybe the bandwidth of your noise?
Well, for a true white noise process, the bandwidth is infinite, right? Because this never decays. So a white noise process is one that isn't even essentially band limited. It is all kinds of unband limited. But think about comparing two different noise processes. X, say in red here, and Y in blue. At any given time, the likelihood that Y takes a large value is higher than the likelihood that X takes a large value. And yet they both appear to have 0 average, 0 mean. So if you had to tell me a random variable is more likely to take larger values away from the mean than it is to take values close to the mean, what would you say about that random variable in like those two random variables? One has all its values close to the mean, 0 in this case. The other has values that can often lie far away from the mean.
The greater range, or yeah, well, it's very.
There's a vocab word I'm looking for here from stats.
Gaussian?
So we haven't talked about the distribution. I'm just talking about the likelihood to be far away from the average.
Variance?
The variance. So Y has a larger variance. So sigma y squared is bigger than sigma x squared. And this is important because the variance of the random process means that you're more likely to have peaks and valleys that are large, far away from the mean. And if those peaks and valleys are large, what happens when you square them? You get an even larger value. So that means the area under the square of this function gets even larger. And so that's the argument for why this level is proportional to the variance. Right? A larger variance of the random process will have a larger power because it's in the time domain, its samples are more likely to be large numbers. Okay, so that's a significant amount of foreshadowing. We are going to talk a lot about Gaussian white noise processes. And when you say that full phrase, that all of a sudden gives a concrete meaning to the distribution at any given time. So when we talk about Gaussian white noise, that means that x of t follows a Gaussian distribution. Okay, for every t. And then because it's ergodic and white, this is true for any point in time. Like this is not a function of time. Okay, let's get back on script unless there are follow-up questions on this. Okay, so the conclusion of our 314 review is now to talk about what's called angle modulation. And so the key, I think, to understanding angle modulation is to stop thinking about sinusoids as sine omega t plus theta, and to start thinking about them in terms of sine of some function of t. Right? This encapsulates everything you used to call a sinusoid. Everything you used to call a sinusoid was an affine function of t. But now if I allow the argument to the sinusoid to itself vary with time in perhaps a nonlinear way, now I can generalize my notion of angle and also of frequency, which is where it actually comes in. So this picture is from the Lathy and Ding book, and it shows what the instantaneous frequency would look like. Sorry, instantaneous angle. So this is a total angle, theta of t. If we had everyone's favorite sinusoid, which is what I've got here, then theta of t is a straight line with a potentially non-zero intercept. Okay. However, if we allow theta of t to vary from a straight line process, then we can still define the frequency of the wave, at least the instantaneous frequency, as the instantaneous change in this angle. So instantaneous frequency is change in total angle, and formally d theta dt. Okay. So now we can talk about sinusoids whose angle is changing with time, but also whose frequency is changing with time. So the other Piazza question was actually just lifted, I think, from this this slide, and the answer, what it means to say this is phase modulation and frequency modulation are so similar that if we were to teach you one and then teach you the other, everyone would die of boredom. That's a fact. They're so similar that there's no reason to not develop them in parallel if you don't like concurrently or tandem than in parallel. So we're going to develop them in parallel because they're so similar. And the argument for why they're so similar comes exactly in here. So in phase modulation, the message changes the phase with a fixed frequency. So we fix the frequency and we let the message affect the phase. If I differentiate this, I can get expression for the instantaneous frequency, which is a fixed carrier frequency plus the rate of change of the message signal itself. Now, so in phase modulation, I kind of start here and work my way down. In frequency modulation, I start here and we're going to work our way up. So in FM, the idea is that the message directly affects the frequency. And so how do I get the phase out of this? I take an integral. So the whole idea is that I can write the instantaneous frequency of both of these schemes because they're both a fixed frequency plus a scaled version of another function in time. Now, whether that function is the message itself or the derivative of the message, then it matters whether you're talking about FM or PM. But if you just take a big step back, these are both fixed numbers plus scaled versions of functions in time. Okay, so if I can phrase all of my derivations on sinusoids whose frequency are fixed plus a scaled version of a function of time, then I can make conclusions about FM and PM concurrently, simultaneously. Okay, so that's I guess the other thing is the other really nice picture that I like to have in my mind when talking about this is, let's say I have a message, and if I integrate that message and then pass the result through a phase modulator, then what I get is an FM signal. Right, so one way to think about this cascade of systems is a frequency modulator. Right, so that's what we talked about from going from here up to here. Now, alternatively, if I take a message signal and I pass it through a differentiator, and I pass the output of the differentiator into an FM block, some magical system that frequency modulates, I get a phase modulated signal. So that means this is one way to describe a phase modulator. I like this because it has this recursive nature. If you want to build a phase modulator, you can get there if you have a frequency modulator, and vice versa. If you want an FM, as long as you start with a PM, you can get the FM. Okay. So this is the other argument that analyzing one of these paths is going to tell you a lot about the other path because it's found in the other path, right? If I know something about the FM block shows up right here, which means it'll tell me something about the phase modulator block. Okay, so the reason, I think the reason that we start with AM and then go on to FM in Intro to Communications classes is because there's this nice mapping within the FM analysis back to AM. I mean, also there's like historical reasons that it started AM first, but let's do this quick derivation. So I'll give you some message signal, m of lambda, and I'm going to define the running integral of that as a new function a of t. Now, I'm going to do something that seems on its face really, really strange, which is I'm going to put that a of t as the phase modulator in a complex exponential. right? So A of t is going to dictate the complex phase in addition to a fixed frequency up here. Now, I'm calling this with a hat because I hope you see that the true FM signal is going to be the real part of this. Right? If I break this up into its Euler's form, then the real part will be a cosine omega ct plus kfa, and the imaginary part will be some j times sine. But at the end of the day, I want to take the real part of the right-hand side. Okay, so if I've got the sum of two things in an exponent, then I can split those into the product of two exponentials. And I think there's a typo here. I think there ought to be a j up here. So heads up for those of you following along at home. There's a typo. There should be a j in the second exponent. Okay, so speaking of Euler, here we go. I'm going to take the first exponent and split it into its real and imaginary parts. And then I'm going to take the second exponent and do something probably not as familiar as Euler. I'm going to use the full, Taylor series expansion. So this is e to the j x is 1 plus x plus, I think it's x squared over 2 factorial. Do you remember this? Remember good old Taylor series?
Yeah, somewhat.
Yeah. That was a rhetorical question, actually. I don't know what to do if you don't remember it, because I don't remember the derivation. So let's just all smile and nod. Yeah, so all I'm doing, actually this is just e to the x, isn't it? Yeah, this is one way to write an exponential, any exponential. Our particular exponential has a complex x. And so that's why this positive sign turns into a negative, because I'm squaring the j, et cetera, et cetera. Okay, so what we get is 2 terms times an infinite number of terms, which gives me twice infinity number of terms. So we're going to be here a while. Just kidding. No, we're going to take the real part of the right-hand side, like I promised. So we're going to take the real part only, which means the terms that had a cosine times a real thing, we end up with them. So there's cosine times 1, and there's cosine times negative a squared. But also the terms that had j times j. So here is j sine times a, ja. And then here is j sine times j to the 3, a to the 3. Okay. So how I promised that this would end up looking like amplitude modulation. Well, does it? I think it does if you start ignoring high frequency components. Or if you start ignoring small components, right? Because these are actually all at the same frequency, omega c, omega c, omega c, omega c. But I think, I mean, so on its face, this is amplitude modulation, right? This is a function modulating the amplitude of that sine. This is another function modulating the amplitude of that cosine, et cetera, all the way down. But the magnitudes of these functions, as you go further and further out in this sum, get very small because of our old friend factorial. Yeah. So if a of t is bounded, and why would a of t ever be bounded? Well, certainly not if the message stays positive. But if the message spends as much time above as below 0, right? If the message has maybe 0 DC component, then it's not so hard for me to believe that the integral of that message will end up being bounded. Does that not sit well with anyone? So if I know A of t is bounded, then I know that there exists an index where that number, that maximum value of A, even when you raise it to a polynomial power, when you divide it by a factorial, vanishes. And the argument for that is that x to the n in the limit is bounded by n factorial for any x. Okay. Now this is a very dubious statement for me to record and put on YouTube, because this is a very loose statement. But as n goes to infinity, this has to hold true, this inequality, for any x. Okay. So what do we got here in the frequency domain? This is so far all in the time domain. Well, this guy gives us a pair of deltas. So this is a over 2 at omega c, plus or minus. This guy, well, that's multiplication in the time domain. So we are going to get, well, this is AM, isn't it? This is double sideband suppressed carrier. Right? It's a function times a carrier. So what we get is this is the bandwidth of A, or twice the bandwidth if you like. But that's what I'm getting at. This is, if you understand AM, that's the key to understanding bandwidth of FM. Is because nestled inside of FM is a whole bunch of AM. Now, this is a kind of interesting fact, is that once we start to get to these square terms, actually, I think this is a question I'm asking my 328 students. Maybe I should ask you. If I have a band limited signal and then I square it, what do I do to its bandwidth?
It's doubled.
Yeah, because I'm going to convolve two things that have finite width, which means the result will be twice as wide. Excellent.
That's actually, you're asking us that. Homework, but that's all right.
Oh, and your homework as well. Oh, there's crosstalk between my classes. All right, well, there you go. There's your answer. So this ends up being, if this is twice the bandwidth of A, this is 4x the bandwidth of A. But these humps are getting smaller, yeah, because of the factorial. So it's not as clean as AM, in which you're just taking the humps and you're setting them out to the carrier frequency. You're doing that once, but you're doing it again with a smooshed out version or a squidged out version. Those are technical terms. Those are good ones. Any questions on this? It's looking like chicken scratch now that I look down at the board, but I want to make sure everyone follows. Okay. So how can I actually derive the bandwidth of the resulting signal, right? How do I know how many of these terms to include before they get negligible? Well, that's a really hard question to answer. So in general, we talk about just the one term case, and then generalize that to more terms. So I guess, yeah, we'll stay here. In narrowband, FM, the key is that's equivalent to truncating at n equals 1 term. Now, why is that true? Well, if it's a narrow band signal, that means think about the message signal as being maybe a single frequency. Then the integral of a single frequency message is also a single frequency, the same frequency. And so A of t is certainly bounded. It'll be bounded by no more than the amplitude of the message, divided by the frequency. And so the argument is that the amplitude squared gets real small, especially when you start squaring and cubing and whatnot. Okay. So then if all we do is we truncate this after n equals 1, including the n equals 0, then what we get is it's a single sideband and then a carrier. Sorry, a double sideband and then a carrier. So then the bandwidth for narrowband FM is just 2b, because we're stopping here, and we'd end up adding the carrier, and so this has a width 2b. If b is the bandwidth of the message. Now, some of you are saying, well, wait a minute. This is modulating by A, which is different than the message. But if I integrate a signal, then I don't ever expand its bandwidth. Think about the Bode plot of an integrator. And if I multiply that by something that has bandwidth whatever, then I'm never pushing that high corner out. Okay, so then because of this integral, the bandwidth of A is always less than or equal to the bandwidth of M. That's a good factoid to memorize. Okay, so when you start talking about wideband FM, then we have to start talking about how wide of a wideband. And so the metric for that is in these modulation indices, which are defined slightly differently for the two. But the idea is that just like in AM, the amount of the thing that we are apportioning to vary with our message, in AM it was the amount of amplitude that we were going to let vary with the message. In FM, the modulation index measures how much of the fixed carrier frequency we are allowing to vary. Okay, so that is called the frequency deviation, and it is proportional to the extents of the message, right? So the peak value of the message is going to be defined as the maximum value of the message over all time. And then the amount of frequency deviation is proportional to that peak, right? Because in FM, the signal is, so phi FM, it was, say, A cosine omega t, where this is omega c t plus kf times the integral of the message. Another way to write that is the instantaneous frequency, omega instantaneous, for FM is simply omega c plus kfm. So if the message is always 0, we're sitting here at omega c. If the message jumps to a maximum value, then the instantaneous frequency jumps to omega c plus kf times mp. Okay, so this, the amount that this can change, this quantity over here, that's our frequency deviation. Okay, and if you were to redo this analysis in phase modulation, everything mirrors what I just said, except we're looking not at the message signal, we're looking at the derivative of the message signal. But the idea is that in a phase modulated system, the frequency deviation is also relevant because we are, after all, talking about bandwidth, which is a deviation in frequencies. And so I think I may have, yeah, this is another typo. I think I called this KP on the first FM slide. Okay, so once I unify these two things and talk about them in terms of their frequency deviation, now I can then talk about their modulation index, which is this beta. And there's this weird factor of 2 pi in there because we have to have similar units on the top and on the bottom. So if this is in rads per second, then this entire thing should be in rads per second. So beta is unitless. But if you're doing this if everything is in hertz, then by all means do not include a 2 pi in there. And so what I like to think about the angle modulation frequency deviation, or the modulation index for angle modulation, is how far from omega c are we going to go relative to omega c, right? So beta tells me basically how far around omega c we're going to go. So therefore, if beta is small, then we have a kind of a small frequency deviation, which means our net FM bandwidth is going to be small. But that means we're also compressing a lot of information into a narrower band. So it makes it harder to decode or demodulate, if you like. And so I'm probably skipping at least 3 weeks worth of 314, I think, to end up with this kind of compromise. So I don't know who Carson was, but this is a pretty sweet deal to get your name tacked onto this. Carson's compromise. I kind of like that. And it's a compromise between narrowband and wideband. In narrowband, the bandwidth of the transmitted signal just depends on the message bandwidth. In wideband, it depends on the frequency deviation. And so what Carson's compromise does is it says, you know what, let's split the difference, let's add them up. Let's call the bandwidth of the modulated signal the sum of these two things. Okay. Oh, let's see here. We've got 5 minutes. Should we talk about tone modulation, or should I open the floor to questions? I don't think we're going to have time to get started on the problem set, but I will give you some agency to tell me what to do here. Okay. Failing to have any questions from the crowd, we can tack on one more thing here. Omri, was that a question or no? Okay. So let's get rid of all this crud. Oh boy. Okay, so we talk about tone modulation. That is, the message is a pure tone. Modulation. So in this special case, the message is, like, we call it a special case, and it's kind of this, why would you ever do that? But remember, we are reviewing all this so we can get to digital communications. And in digital communications, you only need to send a 0 or a 1, which means at the heart of digital communications, there's going to be 2 signals that we need to choose between. So if a 1 bit is, say, message 1 frequency, and a 0 bit is message 0 frequency, then being able to do tone modulation for a single frequency is actually half the battle. So it's not, I think there's a danger of not giving 314 content enough credit because it is the foundation of everything we're going to do in this class. Okay, so we're looking at the running integral of this, which scales it, omega m, turns it into a sine. And we'll say that the complexified xm signal is a times the exponential of all of this stuff. Make a carrier plus modulation factor kf times the integral of the message. And what does this mean? This means that our message bandwidth is omega m rads per second. So if you want it in hertz, this is what omega m over 2 pi hertz. So our frequency deviation, delta f, is going to be the, what do we just say? Kf times the peak value. So Kf times the peak value of the message, which in this case is alpha, divided by 2 pi. So if you go through the arithmetic from the previous slide, you can work out that the modulation index for this specific case is Kf times alpha over omega m. And what else can we do here? We can go back to the time domain. We can talk about this as being the product of two complex exponentials. And I can use my substitution for beta here to talk about e to the j beta sine omega mt. Now, what's kind of crazy is that this function is periodic. I know that the sine is periodic, like that's not crazy, but when I take an exponential and I raise it to a periodic function, the resulting function is still periodic. I guess that's not too earth-shattering if you think about it for a little bit. With period, just 2 pi over omega m, so same as the period of the exponent itself. Now, the Fourier series coefficients of this, so Fourier series of this complex exponential says that this time domain function looks like the sum of a bunch of other complex exponentials whose coefficients have this really funky form. So 1 over 2 pi integral minus pi to pi of e to the j times beta sine x minus nx dx. And good luck doing that integral. Literally, you cannot get a closed form for it, but it is tabulated. It's even given a special name. This is a Bessel function of the first kind and nth order. So this is called, well, it's given a symbol, j sub n, as a function of beta. This is a Bessel of first kind, nth order. And these are widely tabulated. You can look them up wherever you like. And the long and the short of it is that when you get the Fourier series coefficients for a periodic function, that gets you the ability to talk about the Fourier transform. So that means that x of t, our actual FM signal, All right, once I take the real part of all this, is the amplitude times the Fourier series and if I'm taking the real part of this complex exponential, I only get cosines. That's where these cosines pop up from. Which means that in the frequency domain, we're going to have the carrier, and we're going to have side lobes every integer multiple of omega m away. Right, so here's our carrier, and here's -1 omega m, -2 omega m, 1 omega m, 2 omega m. The amplitudes of these side lobes are controlled by these Bessel functions. And the Bessel functions, luckily, are decreasing with n. Okay, so that's why we can say that this is going to peter out eventually. Now, how they peter out is dependent on beta, but you'll see these plots of Bessel functions for different n's and different betas. And so depending on your modulation index, the rate at which these decay will be different. So smaller modulation indices means these decay faster. So smaller betas means j of n as a function of n decays faster with n. All right, we are over time, and I apologize for that. But I promise I will not yak at you on Friday. We're going to do small group work. So if that floats your boat, please come. If not, you're free to do problem set 2 on your own. Thanks, everyone.